Hello everyone, my name is Chenyu. I'm a scientist at Uber Experimentation team. Yeah, really excited to be here today to share some of our recent experience of building XP monitoring at large scale. At Uber, and I believe in many companies here, we really use experimentation to uncover causal impacts. For example, we want to learn, if we reduce the app crashes, can that help us retain customers? Without experimentation, you might find something weird in the past data that users who have more app crashes actually are going to stay longer, but that is probably misleading. We only have correlation here, not causation. Having more app crash and staying longer can be just correlated with heavy usages. So there's no causal links you can build with that. So how do we establish the causal links here? We use experimentation. A/B experiment is probably one of the simplest but also powerful tools to do that. You select a target cohort, you randomly assign them into treatment control, which will be identical other than just the treatment you give them. And that's how you can isolate the causal impact. At Uber, my team works on a centralized A/B testing platform. And we built that in 2021. And since then, we have been powering tens of thousands of A/B experiments every year, helping our internal teams to test and innovate on their product. So the idea of A/B experiment is simple. The basic steps of running an A/B experiment is also very simple, right? In our platform, we provide a series of self-serve tools to help teams go through this XP lab lifecycle. They first go to our power analysis UI to plan their experiment, and then they go to our configuration UI to set up and roll out their experiment. And then in the end, they can analyze the results and conclude their experiment through our analysis UI. So we're all good if things go as we planned, but we all know things really go exactly as we planned. Many things can go wrong during the XP rollout, during the XP runs. And in the past, we have been relying on teams to do their own diligent checks and monitoring for their XPs. And this is where exactly the things can go wrong. Two typical cases we see all the time. People run their own checks without considering the peaking issue. They end up finding more noises than real signals, wasting so many times just to chasing those noises. In the other cases, those checks sometimes is not enough. We still see from time to time the XP rollout actually harm our marketplace without being noticed in time. Among all teams' manual efforts, they can use one of the tools from us, the on-demand analysis tool. So a little bit context here. As we started in 2021, we decided to first build this on-demand mode because we need to accommodate so many different teams to explore their experiment results. There are so many metrics they want to look at. There are so many user types in their experiment. And to think about there are also like different job types that run this experiment. We have not only data scientists, perhaps only 1/3 of them analysis is run by data scientists. There are engineers, there are operational teams, there are PMs that run those experiments. So we believe this on-demand mode gives them the most flexibility. So we have this analysis UI there. They can, whenever they want, they can go to our UI, customize the cohort and metrics of their experiment, trigger the analysis job anytime they want, and then get high quality results, which is guaranteed by our solid statistical package, metric management system, and most fresh data, because we always repull data whenever they trigger a new analysis. But yeah, this cannot solve the problem we just talked about. Our on-demand analysis is still just to take care of the final analysis, but if people use it to run frequent checks, they're still going to get into some peaking issues. Also, it's far from providing timely visibility if we still rely on people to run their own checks with our analysis. So starting last year, we have been making a huge step towards a unified approach for XP monitoring. Essentially, we have replaced the fragmented team-by-team XP monitoring practice with a single centralized platform. So everyone now follow the same process, track the same metrics within their organization, and trust the same results from us. In particular, our new sequential testing inference clearly distinguish real signals from random noises. So now frequent checks will no longer inflate false positives. We also scale our XP monitoring very efficiently. So now we are covering, we automatically generate monitoring reports for most of the A/B experiment across teams. So in today's talk, I want to focus on these two aspects of our system. How we build the anytime valid inference to maintain a desired false positive rate during continuous monitoring, and how we scale our system to reach large coverage with limited resources. Combining these two efforts, we have been able to minimize the risk of running experiment, accelerating its speed, and also help people make more confident decisions. Before I zoom into these two aspects, I want to give you an overview what our system, XP monitoring system, looks like and how it fits into our existing infrastructure. The new things or the things that we updated have been marked in blue here. So we first built a new monitoring backend responsible for syncing eligible experiments, applying monitoring policies, and schedule analysis round at a regular basis. We also took a major step and major upgrade for our analysis backend and analysis package. So now we can batch process many different metrics and XPs at the same time. We also built a dedicated new monitoring UI to provide a better user experience. So besides still delivering all the reports to our existing UI to the on-demand analysis UI, we now have a unified view for teams to explore and see all the latest updates about their XPs in one place. So we basically build a layer of continuous monitoring on top of our A/B testing platform so we can automate frequent checks and also maintain the desired results. So now I want to talk about our science solution to solve peaking problems. What we find in data is that it's very, very natural that teams want to check how their XP is performing even during the early periods of their XPs. In our database, most of the experiments already see their first analysis run through us, even within the first or second weeks since the XP start. But again, our on-demand analysis or their custom analysis, most of them are not built for, only built for fixed sample size, final sample size, not built for sequential testing case. So what is very common for us to see, people get very excited about some improvement, which turns out to be just noise. They could, on the other hand, they could be alarmed by some so-called degradations, and they spend a lot of time debugging these misleading signals, and eventually only the rollout of the XPs or the new features is delayed. I want to illustrate this with a simple example here. Suppose we want to test if the coin is fair. By flipping it 100 times, track the count of heads versus the count of flips. So here with simulation, I show you one run of such. So at the end of the 100 flips, you can see that even at the end, the fractions of heads is not exactly 0.5, which is expected because we know they jump around due to randomness. But that's fine if we only plan a one test in the end. In this binomial test scenario, it's very easy for us to come up with a boundaries around 0.5, and we should expect the final result, the final fraction, will fall into this bound with very high possibility if the coin is really fair. So I'm showing you the 20 runs in my simulation. As we expect, most of the case, we make the wrong decisions. We correctly label the coin to be fair and only incorrectly label the coin to be unfair 1 out of 20 times. But what if we do continuous monitoring? What if we keep testing every time we flip, apply the same statistical procedure at every step? Now we're gonna mistakenly label the coin to be unfair 4 out of 20 times. That's inflating the false positive rate by 20%. And we can confirm this with our real A/B experiments. So we instead run some real-world AA test. The way we do that is we took the XP, each real XP data, and we re-randomize users into new treatment control groups. So we're creating our own fair coin here. So we know the true infect is 0, and everything we detect there will just be noise. And then we monitor those, we do this A test 30 on a daily basis for those XPs. And at the end of the 30 days, we look at what is the cumulative false positive rate, which is the fraction of XPs that already show some statistic results for a given metric. So on average, we see, you can see here, we have, if we use the regular inference, the so-called fixed sample or fixed horizon inference, that false positive rate will be inflated to at least 15%. Even it should have been 5% based on our test level. And this is already the best case. We see even worst case about 40%, or even 80%, depending on what the metric measurement window you choose, and depending on whether you want to include the segmented results in this measurement. By the way, you might find it very strange that there's some dip in this time series trend. So the reason is that when we did this AI test, we were also debugging our monitoring system. So some XPs that should have been added in the beginning only added during the middle. So again, things not always go as you planned. So we need a solution to maintain a desired false positive rate. It doesn't have to be 5%, but we need some sort of guarantees from a platform perspective. And there are two main approaches for this. One is group sequential design, and another is anytime valid inference. Group sequential design is very common in clinical trials. You need to plan your experiment very carefully. You need to predefine how many checks you want to run during the XP, and when you need to run them. Usually, it will give tighter confidence intervals if the number of checks is small, but you cannot exceed the scheduled runs, or do some real continuous monitoring. If you do that, all the bets are off for statistical guarantee, and the computation can be very complicated due to those multivariate integral things in group sequential design. For anytime valid inference or anytime valid confidence sequence, it's very natural tool to support continuous monitoring. So you can peak at any time and stop at any time. The computation is very straightforward. And also from our large-scale simulations, we don't find major concern in terms of detection speed over the typical sample sizes and typical infect sizes for our A/B experiments at Uber. So we decided to adopt anytime valid confidence sequence along with this monitoring system. For this confidence sequence, basically it's a sequence of confidence intervals that contain the true infect with design probability at all times, rather than just at a fixed or final sample. The basic idea is that in sequential testing case, we're dealing with a stochastic process. So both point estimates and confidence intervals, they evolve sequentially over time as new data arrives. So as I show you in that coin flipping test, the fixed horizon CIs looks like they shrink too fast compared to how your point estimate concentrates to the true infect. So we know at some point in time, this fixed horizon CI will not be able to cover the true infect for sure. The anytime valid confidence sequence, on the other hand, they shrink in step with this underlying stochastic process. Basically, it's a martingale-based approach leveraging Veil's inequality in this trend of literature. So we need to construct a non-negative martingale from our estimator and variance processes. And using Veil's inequality, it can guarantee the coverage at all times. Here I list the statement of Veil's inequality. Basically says, for a non-negative martingale MT and a threshold A, think about A as your desired type 1 error rate, the probability of this MT ever exceeds A across time will be bounded by the expectation of starting value divided by A. That's how we get the guarantee of the coverage of the true infects over time. In practice, we implement this anytime valid inference with Gaussian mixture boundaries. We generalize it to our OS estimator in A/B experiment setting. And basically, it provides a z factor, as I draw here, as two examples here. It will be very conservative at the beginning, but it will drop and then grow very slowly over time. Compared to in a fixed horizon CI, you will always see a constant z factor there. So this works as a counterforce of avoid shrinking too fast. Another benefit of this is it allows flexible tuning. With a tuning parameter, we can decide for different XP type or different metrics, we can decide to make the bounds tighter initially if we want to detect some meaningful impacts early on. Or we can be more conservative from the beginning if we expect a long experiment setting. So what it looks like in practice, I want to show you some shadow testing results when we compare the regular fixed horizon inference and our new monitoring inference with anytime valid confidence sequence. So for shadow testing, we ran both actual A/B test and the re-randomized A test, as I just mentioned, for the subset of XPs and metrics. So for real A/B monitoring analysis, you can imagine everything we detect there at statistic will be a mix of signals and noise. The problem is we don't know the exact split of them. This is where the re-randomized AA test result comes in to help, because we already know everything we detect there is pure noise. So if each real XP have their corresponding AA test, we will get some sense of the real signal captured by each inference methodology. So here I show on the left-hand side is the fixed horizon inference, regular inference results when we track this XPN metrics for 30 days and track their detection rates. And on the right-hand side is the monitoring inference results. First, note that how in both plots, the difference between A and AB test remain roughly 8% on average. This means that on average, we really didn't lose much signals. But as you can see, we lowered the false positive rate from 15% to less than 1%. So we successfully filter out the noises in those continuous monitoring. As a result, the teams will not constantly bothered by those fake signals and chasing fake misleading results, and they can make more confident decisions with our results. I want to conclude this section with a real-world story. This is before we launched our monitoring system. In one of the XP team do their own checks. They found something, but they really couldn't determine whether there was a true degradation. So there are back and forth discussion between their engineers and data scientists for 10 days before they finally stop their XP. One thing we do is we test it with our system, and we find out our system actually can flag this to them 3 days into the rollout, even with just a 1-day metric data and 5% test level. This means we can help them make this rollback decision much earlier and stop this harmful XP rollout much earlier. Okay, in this next session, I want to talk about how we scale our monitoring to cover many different XPs and metrics with batch analysis solution. As I mentioned, we used to rely on teams to do their own checks. Some teams set up their dashboard, just track some time series trend. Some teams, they only spot checked on their results. This is, obviously this takes a lot of manual efforts, but also more importantly, this inconsistent practice creates real vulnerability to mistakes. In one of the previous example, in this XP, find some significant degradation, but it went unnoticed for days because the teams put up the wrong queries for that metric, for that key metric in their dashboard. Also, we learned afterwards that, as you can see here, the degradation doesn't happen at the beginning. It happens during the mid-run through the XP. So even if the team have the right query, if they don't do the diligent checks, or they fail to attribute that time series change to their own XP, they could still miss it. So we want to provide timely visibility at scale with our XP monitoring system. But to do that is very challenging. Imagine how many XPs and metrics we need to run at the same time. Potentially, we need to rerunning them at least once per day. And we also have a plan to extending that to multiple times per day. This will be very expensive, very slow, if not optimized. So before, as I mentioned, we only have on-demand analysis to give people most flexibility to explore the results. But this actually give them, also create some duplicated efforts. As I illustrate here, even if the 3XP look at exactly the same metric, we have to create the separate jobs, Spark jobs for them. And in each job, they need to separately put their own cohort and repeatedly read and compute the metric data. Think about if thousands of such jobs hit our computation cluster. We have seen this not only create slowness, it's also create the reliability issues, with a large scale of analysis failures. But we also identify that there's a new opportunity for us for a more efficient analysis solution because of the use case of XP monitoring. In XP monitoring, after we discuss with different organizations, we always predefine the metrics and the configurations. And for many of those key metrics, they are overlap across XPs, especially within the same organization. So we built the batch analysis solution where we can combine multiple XPs and overlap metrics into one job, so we only pull the common data once, and also we can batch compute large number of results in the same job. With this approach, we constantly see at least a 5 to 10 times reduction in computation cost and the time, while we still maintain very high success rate for our monitoring analysis. Yeah, so here, let's take a deeper look at how we handle data in this batch solution. So now we batch multiple XP configurations into the same job. So instead of each XP pulling their own cohort request, we unify all the cohort requests into one query, and also one query per metric. So we greatly reduce number of queries we need to hit to our computations cluster. At the same time, we reduce a lot of efforts in teams' efforts. So, but when we now pull a lot of data set, larger data sets for all the XP we batched, it also means we need to now compute a much bigger set of results for all the XP we batched. So this is where the batch OS comes in to compute the final results. So again, a little bit history about what we were doing before. With on-demand analysis, we have a standard approach. We just use Spark building ML library to estimate a full regression adjustment model. We didn't choose other popular choices like qubit because after some simulations and validations, we find out a full regression adjustment model can help us more reliably account for sampling variations and also help us more efficiently use pre-experiment data to improve the precision of our estimation. But to support this complex modeling, we need to repeatedly initialize this black box algorithm in our Spark job. And this Spark job, creates a lot of overhead, and it's very hard for Spark to understand the procedures and to optimize the procedure in its natural way. So we decided to, along with building the XP monitoring system, we decided to rebuild our stats library. Now we have built our own stats library for the same regression model estimation, but in a more batch-friendly and scalable way. So as I show here, now we can batch multiple XP and configuration data at the same time into one unified data. We break down the main computation into 2 steps of aggregations. In the first step, we just get the first and second moments from the data to estimate the OS parameters. And in the second aggregation, we use the estimated parameters and the data to get the residual moments to compute the variance covariance metrics and eventually get the inference, the confidence intervals and p-values. So now each aggregation operation is very heavy, but this operation is very straightforward for Spark to understand. So Spark can do its own native optimization. And as a result, we have achieved massive parallelism. A batch analysis job that used to run 5 hours since we need to compute many different XP metrics dimensions, in total thousands of results, now only took 6 minutes in computation. This is exactly what we need to scale our monitoring system to cover many XPs and metrics. Yeah, so this is pretty much what I want to share today. To wrap everything up, previously we had teams separately run their own checks, inflating a lot of false positives, and also lack a shared source of truth across the company. Now, with our XP monitoring system, we can have teams just leverage more reliable insights, so they can check their experiment whenever they want and iterate quickly. We significantly reduced the IC time on experimentation every month, and more importantly, we're going to stop the harmful XP rollout much earlier. What's next for us? We are extending the coverage of XP monitoring to more use cases, including we want to expanding from a continuous monitoring to continuous experimentation, meaning that we want to enable teams to be able to stop their XP early and make product launch decisions with better confidence. Yeah, so that's it. I want to thank everyone to attend this session, and also my colleagues and Sean, especially, and also Sean here. Thank you.